Okay, hi everybody. It's great to be here and have the chance to talk a little bit about things that my team and I have been working on for recent time, and this software that we built around it. So data evaluation, first this needs to work. Data evaluation, what is it, right? Let's first try to fix some ideas. What we're interested in here is in what is the contribution of training points to one of two things. Okay, we want to look at what a training point does, for instance, global accuracy of our model. Okay, so overall model performance, and we want. So we don't want to like restrict ourselves to accuracy or anything, just global model performance. We can look at things globally or just at single predictions. Okay, we're going to be talking about the two things in this talk. I will be presenting the first, and Kristof is going to be talking about the second one. For the purpose of this talk, we're going to refer to the first part as global methods, although this is by no means established in the literature or anything like this. It's just for the talk. And for the second one, we're going to be naming this local methods. Okay, so for the global valuation methods, I think it's good to have a little understanding of what this means to evaluate points or to value points. So we're going to explain just real quick what it is that, a very simple way of doing this, which is first defining an object called utility. And this comes from cooperative game theory, which is a field which started many of the methods that we're going to be talking about. So we define a utility, which for us is give me some data. I train my model on it, a supervised model, and I score my model trained on this data on some fixed validation set. Okay, this is my utility. How good was the data for me? This is for any subset of data that you give me, but the validation set is fixed. Okay, now I take one of my training points, I fix it, and I'm going to look at what this training point did for my score, for my utility. So first, I compute the utility on the whole training set, taking this point into account. It is included. Then I'm going to compute the utility without this training point, so I remove it. And then I'm going to compute the difference. So I just accuracy without the training point that I'm interested in. This is the little pseudocode. And this intuitively, I mean, it's clear why it's called leave one out. It's just remove one point and look at the accuracy. Basically, the value of point X is the utility at the whole training set minus the utility at t minus x. So what's the intuition here? If removing my point made the utility go up, it was probably a bad point, right? So I want this thing to be negative, and the other way around. Okay, and I did this for one training point, which means I need to retrain n times in order to compute the value of all n points. It's already pretty expensive, but it has a bigger drawback, which is that this has very low signal in the sense that if you have 10,000 points, usually removing one is not going to tell you much. So this method, leave one out, is not really used in practice. What people do is they look at subsets. Now I'm going to do this in and out thing for all possible subsets of the training set. This is some pseudocode. I just sample subsets. I score with and without, and then I compute a weighted mean. Okay, you can gloss over this. It's not so important. This gives rise to a family of methods called semi-values. One of them is data Shapley, which started this whole thing in machine learning like 4 or 5 years ago, or maybe a little bit longer. So formula here, I mean, the key thing to look at is that we have a sum over all subsets, which is pretty expensive, as you can imagine, and means 2 to the power n minus 1 retrainings if you do this naively. You don't do this naively, of course. So, okay, we have an intuition. It's about removing points and adding them back. This is one family of methods. There are many others which don't use this approach, but this is like the starting one. Okay, we have this. What can it do for you? We have this example out of our documentation where we take the top hit Spotify data set. We want to predict song popularity, okay? And we do this with a simple gradient boosting regression regressor. Okay, and now we do this thing of adding and removing points on all subsets with some magic in the background. I mean, it's not magic actually, but we do this for every training point. And now we sort them, right? We take the lowest value ones, the ones where we thought, removing them was good. And for those, we drop them. And what happens is that in this training set, for this model and this metric that we chose, we see an improvement in the accuracy just by dropping points. I mean, these numbers, take them with a pinch of salt. I mean, it was a simple model. We didn't do much. So you don't expect to just, hit a button and get 10% more accuracy in everything you do. It's not going to happen. But you see these improvements. OK, and this is done in 3 steps. First, load data set and define your model. We have a split here in train, validation, and test. OK. Now you define some scoring function that you care about, in this case, accuracy. And this accuracy is measured over the validation set and your utility object. OK, done this, the utility wraps the model and the score. So data set, model, scoring, utility. And now you mix everything in one valuation method. This is one example, data Shapley, which is in the library. And you run it with joblib in parallel here with one node backend. You fit this thing. And what you do now is, what I want to say now is that you can change the model for any model that supports a fit method. You can add your custom scorer that you can look at F1 or whatever. You can even not look at the validation set if you're not interested in that. You can then pick any of the evaluation methods that we have. We have like a dozen, a little bit over a dozen right now in the evaluation part. And you can change the backend to Ray and run on 400 CPUs if you have them. So you have this, you fitted your thing, took a while, and now what you do is you take your values, you drop the bad ones, like 100, I don't know, I just picked a number randomly, this is pseudocode of a sort, and you fit on your clean data, and this assertion works. I took a more conservative number here, 1.02, because, I mean, this one is made up completely. Okay, profit. We just won. Now, so caution here, this is our new interface that we're going to be releasing soon, like in hopefully in the next couple of months. Currently, it looks a bit different. So if you go to the documentation, don't be surprised. It's going to look different, a little bit more cumbersome. So what we did, we removed bogus points and we increased accuracy. But it's better not to think of data evaluation as some kind of black box that you hit a button and do something, but how do I choose this threshold and what do I know? It's better to use this for inspection. So now I look at the worst points and I look at them actually and I see, this shows me patterns. This helps me answer the question of what's wrong with my data. So you can maybe look at common features that the wrong data had, and you can use them to maybe even debug your model, because maybe it was looking at the wrong things. So it's an inspection tool. But it also can help you with acquisition. If you have multiple data sources, this can help you pinpoint some of them or one of them that is producing bogus data, and how can you find it among the sea of data points I usually get. Attribution is another technique that that works better with the inference methods that we're going to be talking later. And then in the literature, there's more applications that we're not going to be talking about now. Well, maybe I can say that there's some recent work in improving fairness metrics, where your scorer and the thing that you're interested in are different, and you can maybe improve the fairness of your model. This is some recent work published recently. Okay, so what do you need to do this? Well, first, any scale-and model, or anything that you wrap with a fit. There's not much. Some scoring function, which again, scikit-learn gives you for free, or if you define one, you have the same. An imperfect data set, if you're perfect, what do you want this for, right? And you want to install pyDVL. We may want a better logo, I don't know, maybe. What frameworks? NumPy and scikit-learn, they work. Joblib for parallelization. We use memcached for caching results. And the second part that Kristof is going to be talking about uses mainly PyTorch. We're planning to support JAX, and we use Dask for large data sets. pyDVL is still changing, so I mean it's not alpha, but the changes to the interfaces, I'm presenting the interface now, it's not published yet, so there are changes. So what's the catch here, right? Sounds like too good to be true. I mentioned computational cost. 2 to the power n is pretty bad. Also, because this is pretty bad, I'm going to do Monte Carlo of some, going to be doing Monte Carlo of some sort. So when have I converged? There's another question. Then how sensitive is this to the random seed, to the data split and all these things? There are multiple sources of randomness here. And then finally, this is dependent on the model and the metric that I pick. This is tightly coupled to it. This thing is actually not a problem. This is a feature, it's not a bug. I mean, we really want to examine our model and our metric. So that's not a problem. Consistency across runs, if you think about it and I want to run 10 times and get exactly the same, yeah, it's pretty bad. But it doesn't matter because you don't want that. You want to select chunks of data points and look at them. You're not interested in absolute values that they're meaningless. You're interested in the rankings that they give you and in chunks of data. So the 2 big issues are cost and convergence. And there are some solutions. Well, we have Monte Carlo, as we said. There are a bunch of sampling strategies and a lot of optimizations that happen that help a lot, that reduce the exponential complexity and bring it down to O(n) log n and things like this. There are proxy models. So instead of using your very expensive model that you refit a bunch of times, you use a one which is simpler, like KNN or something like this. And then there are methods that are specifically designed to exploit the local structure of some models, like KNN, for instance. If you use that, because of its locality, you can drop many of the utility evaluations. Then there are others like data OOB that is for bugging methods and doesn't work in this way at all. And there are more techniques that you can use. Okay, that was all for my part. Now Kristof is going to be talking a little bit about his thing.
Yeah, so hi everyone. So Miguel told you something about getting a quality metric for your data, like from a global viewpoint. And I would like to tell you something more about like point-to-point evaluation. Yeah, so having an answer to the question, what is the influence of a specific training point on the output of my model on a specific test point or on a set of test points? And for this we we used a different approach in the library. So what would be like a naive thing to ask? So if I have a data and I would like delete one data point from training, how does the loss on a test point change, right? And then you can compare those 2 terms. Well, okay, but what's the problem? We would have to do again, a retraining for every training point, right? Which you don't want to do. Yeah, think of like a large vision model or something comparable in complexity. And you have like thousands, millions of training points. You don't want to train a model not just for one leave-out training point, right? Okay, but still you want to have an answer to the question, okay, what is my influence from point to point? Well, what can we do? There's a concept from robust statistics known as inference functions. And you can somehow get an approximate answer to this question using an expression like this. What is this? So somehow this is an approximation of the change of the loss of the test point given the training point upweighting, yeah, changing. So it's an infinitesimal measurement, yeah, sign flipped. So if this expression is negative, your loss would go up. Yeah? This is like, there's a mathematical derivation behind it, which like has some prerequisites, which are, well, not always like fulfilled, but at least you can try to compute this. Yeah? And sure, what you get is it's way faster than doing a full model retraining, but still, what you have here is the inverse of a Hessian matrix. So this is the dimension of the parameters of your model. Yeah? So you get memory consumption like n squared, right? And you would have complexity to actually compute the inverse n cube, right? Which is like not doable. So what you do, yeah, you approximate these inverse Hessian vector products with something which is like not computing the Hessian directly, using implicit autodiff computation, plus approximations of the metrics, like low-rank approximations, stochastic approximations of this, and hopefully you end up like in a almost linear runtime. Well, and if you do this, you can ask the question, is this a good idea? Yeah? Can I somehow get value from this? And is the approximation quality actually the right question? Yeah? And this is like an ongoing research topic. To what extent the precise computation of these values is really meaningful and stable. But I would like to show you an example, like what we computed with our pyDVL package, how you could use it on your daily life. So we took a data set from the NIH, which is a malaria. So blood cells infected with malaria or not. So it's a binary classification, vision problem. And the reason we took this is we didn't want to like artificially switch labels and show you, wow, we can detect our own switched labels. But there was a discussion in the forum saying, like, in this data set, there could be some mislabeled images. And how do they look like? So you have like these red circles, dots in the cell, which is a marker for infection. So this is a image of a blood cell. And if you have like these red circles, dots inside, it's infected, and if not, it's uninfected. Right? And the goal is now to, given the values, like you have training points which are labeled infected or uninfected, you have test points which are labeled uninfected, infected, right? You compute these values, which give you like the point-to-point expression for the one has a positive or negative influence to the other one, and this you want to compute. So what you do, you have your model. By now it's torch-based, but we like to include the JAX-defined models as well. You normally train your model. You have your test data, and then you define your approximation. In this case, like this would be the naive implementation. That you really like compute, given your model, given your training data, compute the inverse Hessian directly. So this happens here in the fit step. And as I said, then you get like this point-to-point value, right? Which you can batch somehow. But if you have a large data set, you would like to map this, right, over combinations of batches for training and test data. So we have an additional concept that we somehow map this over batches of data. And then you compute these. So these, the highlighted line, the last highlighted line, is actually this value, this product you have seen with or approximation of this product you have seen. Well, and then you can write it to disk, mapped, whatsoever. So as I said, you don't want to actually compute these Hessian matrix or these inverse. You can do different approximations. So this is like a low-rank approximation, which is projection, single value-based projection. You can use randomized projections. Then you can use a different mapping model. Instead of doing sequentially, you can do it in parallel. If you have like a large cluster, you map this to more worker nodes. And then again, you can calculate the influences and map them to disk. And what we would like to do is to provide like a library which implements recent algorithms, like precondition conjugate gradient, stochastic estimation, and so on and so on. And this is still growing. And the hope is that it helps researchers to benchmark their new approximations on their data sets, and practitioners to easily choose out of the box a good computation model. So we get these train to test values. What can we do for this? So now think of this: for every training point, we get a vector with the influences for every test point. So this is somehow a feature for a training point. Think of this in this way. And now with this feature vector, you can do like anything you like to. In this case, we computed the 0.25 quantile of this values, right? And I said we were looking for the negative ones, like on this side. So no, choose like threshold, look to the left, right, and inspect your data. And what you then get, so this is like when you look from the training labels, which are training data, which are labeled as healthy to the healthy test data set, you get something like this in this low value quantile. So maybe at least you can have a look at it and say maybe these are mislabeled data, right? Same for parasitized. So other way around, you're looking for into the parasitized training data and the influence on the parasitized test data, right? And you get like maybe mislabeled data. But you could also like get training points which could be just confusing. Like the one on the right, it's like a somehow concentric circle, which is maybe confusing for the vision model to be identified as a infected, as a parasitized one, but it's not a silver bullet. You have to inspect this one. And shortly, what are the problems? So the computational complexity is this one. So you have to somehow come up with a method to compute these preconditioned gradients in a like effective way. Then you have to fit all these gradients into memory, right? And this is the restriction you have from the memory side. What can you do? Well, sure. The first thing you should think of is really from the algorithmic side to approximate this product, and for the memory complexity parallelization plus out-of-core computation, because it's completely parallelizable. We said it's point-to-point, and it's independent, so it's completely parallelizable. Right, and then like change your approximation, change your mapping, your calculation. So, for example, if you have like a workstation like a DGX, several GPUs, then you could compute it like this, if you providing the client for your local cluster. Right, and now the last question you have to ask is when to choose which, like scheme to say. And so the inference functions are a good way to at least get a rough intuition. If you have like large models, they have to be, like in this case, you see they have to be smooth. So all this is based on like autograph differentiation, and so this is like a prerequisite you have for the inference functions, which you might not have for the data valuation. You've seen there was a gradient boosting regressor, which would not be possible for this inference function scheme, right? You get a point-to-point variation. So like in our example, like for simplicity, we computed a quantile, but you could have computed like a representation of a training point given the influence features, like, for example, build a second classifier for mislabeled data points. If you, for example, if you know like a test data set which is clean, like really clean, and you have like some systematic errors you've collected, you could train, like given these features on the test set, you could train a classifier for your labeled data, right? For the data valuation, smaller models, it's the sklearn interface, and you get like more global question, like a simpler answer to is the point good or not. And like the last thing to say, it's not a silver bullet. It's an active process. It helps you debugging your data, but it's not like automatically. It gives you support, like well-founded support, but you still have to do work. It's not an automatic process. Did I forget something? Or oh yeah. So this is our team, and we'll be happy to get some feedback from you and or even contributions to our open source package. Thank you.
All right, thank you. Great talk. Are you ready to take some questions? So here comes the first question. How do you ensure that you are dropping bad data and not just difficult underrepresented data?
Yeah, so we're not dropping anything, right? It's just that like you compute scores or like features for your training set, so that helps you to like decide what to drop, but we do not drop automatically. It's like for the example we have shown, like for the cell example, it was really like the top three, like the smallest three quantile values. Yeah, we just plotted, but what you would do is like get like 100 examples from a quantile of this distribution, right? And inspect this manually. This is what you actually would do. Yeah.
All right, thank you. Next question. Isn't there a concern regarding out-of-distribution performance or generalization? This seems a little like the opposite of regularization.
I'm not sure what's meant with opposite of regularization, but
I think they might mean that if it was the same question as the first one, I think, like if you drop data automatically, just looking at these are bad, so I throw them away. The thing is, bad is quote unquote bad is, I don't know, we don't know if it's bad. You just need to look at it because it's hurting your performance. Maybe it's out of distribution, maybe your model is not good enough.
yeah.
You just need to look at it. And maybe there's a pattern that emerges, or maybe you need to look at it. It's not, I mean, maybe the first example was a bit misleading because, oh, you drop things and magic happens. It's not that. It can happen, but not necessarily.
Yeah, and for example, just to add to this, so these values like heavily depend on the optimization state of your model. Yeah? If you're like close to an actual minimum of your loss, they might work more stable. But if you're like far away, which depends on your training process, yeah. So and the influence of this, like not the influence values, but the influence of this model not being completely optimized to the local minimum has an effect as well, yeah. And you can't automatically say or quantify in a good way. At least we are not aware of this.
And then there's the next question regarding another package, which is called CleanLab. In that case, maybe if you heard of that package, can you contrast pyDVL and CleanLab?
So I'm not very experienced with CleanLab, but I think it's more looking at changes in your data distribution when you train, right? Like, so it takes some statistics of your data and then looks at changes in those. Data evaluation is not about that. It's more about inspecting and looking at the data. At least the methods that we present here. It can be used in other applications, but I think it might make sense to include some of the methods of pyDVL into CleanLab, and we've been thinking about that a little bit.
How do you avoid overfitting your scoring function, likely the validation set? Would you recommend nested X validation and increase the cost even further? How to avoid overfitting the scoring function?
Can you how to avoid? Yeah, I mean, yeah, that's a problem. Of course, there is a dependence on the validation set that you pick, and if you're scoring on that, so there's the assumption that is a good one. But again, this would be a major problem if you were reporting errors based on this, or if you were automatically doing some decision based on this, but you're not. You're just helping yourself, you're debugging your data and you're debugging your model. That's how I've used it successfully in the past, not as some part of a black box pipeline with some magic. And it is helpful for that.
There are still questions coming in. I think we do 2 more questions, and then people will probably rush to the lunch, maybe. But,
we are also happy to take questions in our GitHub. There's a discussions page where you can ask.
So maybe 2 more questions. Can inference functions also be used for tasks other than classification? For example, segmentation, inference function for other tasks like segmentation?
Yeah. There's no. Yes.
And pyDVL scores sample contributions. Other packages such as SHAP are scoring feature contributions.
Yeah.
Can I also use pyDVL for that?
Yes, you can. You can change we even have a notebook, I think, that does this. One can use it for that. It's an interesting question because you can think of feature attribution in this direction in your matrix, in your design matrix like this, or you can go data valuation like this, and there's some recent work that does it in blocks even. It's a 2D Shapley, something like this. So we are thinking of generalizing a little bit our interfaces to be able to do all of it.
So we are running over time. Next is the lunch break. If you have still open questions, come here to the front. The room is free, so you can start asking.